Dear organizers of the conference, dear participants, my name is David Gajdoš and I am from VSL Software Company, Košice, Slovakia. Together with my co-authors from VSL Software Company, Košice, and from Pavel Josef Šafárik University in Košice, we prepared the solution for China Physiological Signal Challenge 2021, which was focused on finding atrial fibrillation on 2-lead ECGs. Since we believe that the atrial fibrillation is not the only challenge for ECG classification, at the end of the presentation, we would like to introduce Cordelia, our prototype for short 12-lead ECG classification, which can predict more than 20 diagnostic categories or anomalies in the current version. The first task of the challenge was to correctly classify the 2-lead ECG recording of different lengths into 3 classes: non-fibrillating, paroxysmal fibrillation, and persistent fibrillation. In the final evaluation, which is based on scoring metrics, the plus points are obtained only for correct classification, and the penalization are given for misclassifications. The second task of the challenge was to correctly predict onset and offset of the atrial fibrillation events as paroxysmal signals. We can get 0.5 to 1 point for each start or end based on the correct localization. Moreover, the scoring formula penalizes generating too many predicted events in one particular ECG. Our solution is based on 2 phases. First, we split the signal into 23-second long slices by using sliding window with a shift of 1 second. Then, we solve binary classification task for atrial fibrillation in each of the slices. In the next step, we calculate aggregated numerical feature, which include, for example, number of successive fibrillating classification or percentage of fibrillating slices. Those features are finally classified with the random forest model into 3 classes: non-fibrillating, paroxysmal, and persistent fibrillation. Now we can move to our deep learning model. In particular, we used modified one-dimensional variant of popular ResNet50 that provides binary classification. We processed the 2-channel sequence of approximately 4,600 points, which correspond to 23-second window. The flow mix-up method is applied at the input as it's shown to be beneficial for this task. Since the training set provided in the challenge contains recordings from only 105 patients, and deep learning methods are strongly dependent on data diversion, we have decided to significantly expand the training set of the deep learning model by more than 120,000 recordings from 7 publicly available datasets. However, the final random forest model was trained only on data from the challenge to understand the given labeling. The second phase of our solution is based on localization of atrial fibrillation events. We proposed 3 different approaches or alternatives to solve this task during the challenge time. The first alternative uses output from the first phase. We evaluated the sequence of probabilities from successive sliding windows. Then, we determined the approximate onsets and offsets. In the picture, you can see the sliding window which moves over the signal with a shift of 1 second. If there is an overlap with the fibrillation event, the probabilities rise, and we know that we have found the onset of the fibrillation event. This approach was slightly inaccurate by shifting in comparison with real events. However, more precise solution was obtained by the second alternative. In the second approach, we classify only the individual IR intervals, omitting the QRS complexes. We have extracted the IR intervals using our modified version of Hamilton segmenter for IR peak detection. For the classification, we have used less complex version of deep convolutional neural network as in phase 1, that processed 2 channels and 300 timestamps that corresponds to 1.5 seconds. This network was trained not only on signals from this year's challenge, but we included other datasets mentioned in phase 1. In the picture at the right side, you can see one of the evaluated IR intervals omitting the curious complex. Generated probabilities are later processed by an even localization algorithm by finding at least 5 successive predictions over the threshold of 50% and marking the events. The third alternative was to classify the IR intervals with the surrounding context in a 5-second window. Context allows analyzing rhythms and takes into account very short fibrillation events. We used similar network as for individual intervals, but we processed 1000 points that corresponds to 5 seconds. In the picture, you can see a single evaluated interval as green arrow and the context of 5 seconds surrounding as the red dashed line, which is centered at the middle of an evaluated interval. Same event localization is used as before. Now, we would like to summarize our results on the validation set of the challenge. With the first approach, which used the same deep learning model in both phases, we have obtained the score approximately 1.98. By creating second deep learning model for classification of IR intervals without context, we moved to approximately 2.06 points. Finally, the third alternative provides the final 2.12 points on the challenge validation set. Now we will summarize the final approach, which we selected as the best candidate for evaluation on the hidden test set. Deep learning methods have been shown to work very well for this task. Firstly, we use one to classify the signal sections and to obtain a sequence of probabilities over which we calculate aggregated numerical features. Those are classified by a random forest model in 3 classes: non-fibrillating, paroxysmal fibrillation, and persistent fibrillation. Those classified as paroxysmal are then processed in a phase 2. We classify the individual IR intervals using the second deep convolutional neural network with context of 5 seconds surrounding, and then process it by a simple event localization algorithm. The output is a set of beginnings and ends of fibrillation events. For the deep learning methods, it is crucial to have enough data and quality labels. Unmarked and incorrectly marked events cause several problems, and it would be very helpful to have more databases with paroxysmal signals, such as CeZIS challenge database or the MIT BEH Atrial fibrillation database. We believe that including the large training set has significantly improved the solution. This was the summary of our approaches for this year's challenge. And since we know that atrial fibrillation is not the only challenge in an automatic ECG classification, we have created a prototype for automatic ECG evaluation which currently processes 12 lead ECGs and can predict more than 20 diagnostic categories or anomalies. It is available online at the shown address, and now we would like to introduce it to you.
Cordelia is the application for the automatic evaluation of standard short-term electrocardiogram recordings. 2 main parts of the application are implemented: demo section and section for uploading your own electrocardiogram recording. In the first part of our presentation, we would like to kindly introduce demo section. By clicking on the demo button, the list of 32 examples of electrocardiogram recordings in digital format is shown and ordered by various categories. In total, 21 diagnostic categories or anomalies of electrocardiogram recordings are evaluated in the current version of the Cordelia application. By selecting the electrocardiogram recording, the Submit button can be applied for displaying the evaluation screen. The diagnostic categories or anomalies of electrocardiogram recordings which were evaluated by our application with a probability of at least 50% are shown here at the top left part of the evaluation screen. Moreover, our Cordelia application provides the possibility to view the remaining diagnostic categories or anomalies with a probability of less than 50%. 12 leads of selected recording are drawn by default here. The leads can be filtered by clicking on the switches. For example, if the user likes to see more comfortably the leads representing the diaphragmatic walls, this means leads number 2, 3 and AVF, he can switch off leads AVR and AVL. Another possibility of the application is to change the rendering scale by clicking on the magnifier icon. The original view is shown by clicking on the Show All button. In addition to the medical assessment of the electrocardiogram recording, the Cordelli application also evaluates its technical quality in the form of a simple traffic light. In our demo example, the recording is evaluated by orange color as problematic, and the reasons for this evaluation are given in the more detailed description. In this case, the user should consider the renewal of the electrocardiogram examination. Our application will not evaluate an electrocardiogram recording with a high level of noise, the serious dropout of leads, or the other technical issues regarding the correct classification of diagnostic categories. However, the Cordelli application draws the leads of the selected recording for each valid submission. Now, we can move on from demo section to the section for uploading your own electrocardiogram recording, which has the identical structure of the evaluation screen. This functionality is available from the main screen or by clicking on the Upload Next ECG button at the top right corner of our actual screen. Primarily, the Cordelli application is designed to automatically evaluate 12 lead electrocardiogram recordings in adults, which are saved in WFDB format. The application will notify the user by an error message if the files are of incorrect format or not both required files are simultaneously uploaded. For example, in case it was uploaded only a header file, we can see the mentioned message here. Data file is missing. If both the header and data files are uploaded correctly, the age and gender of the patient from the header file are automatically stored in the application and shown on screen. If these data are missing or incorrect, the user can edit them manually. Finally, we obtain the evaluation screen for our own electrocardiogram recording. There is possible to repeat the evaluation for other electrocardiogram recordings by clicking on the Upload Next ECG button.
You have had the opportunity to see a prototype of our application, but we are already working to improve its accuracy and expand its functionality. As we are interested in semi-supervised learning methods, we are looking for large ECG datasets as shown in the slide. We appreciate any partnership with subjects that find our research interesting, for example in clinical projects or practice. We are also open to cooperation with manufacturers of ECG machines or smart wearable devices, which could be a solution ultimately in favor of patient. Thank you for your attention and feel free to ask any questions now or anytime at the shown others. Thank you very much.